Hi everyone, so welcome to STEM in Places Introduction to Chemistry and Cookies. And this is part 2 of day 1 of the camp, so let's get started. In the previous video, we talked about atoms and how they make up elements, and then how elements make up compounds and molecules. And then we also discussed the difference between physical and chemical changes, and also how atoms bond because chemical reactions happen and atoms form bonds because they want to have a full valence electron shell. So what that means is they want to have 8 electrons on their outer shell of their electron cloud. So right now we're going to be discussing the types of bonds. And so, I find this pretty interesting. So there are 2 main types of bonds in chemistry: ionic bonds and covalent bonds. And depending on what type of elements are bonding together and how many atoms each element needs, and also things like how many atoms of each element there are, we're going to get these different types of bonds. And then the different types of bonds are going to result in different chemical reactions. And that's going to affect how chemical reactions are going to happen and when and under what conditions and stuff like that. So ionic bonds is when one atom gives electrons to another atom. So last time we discussed how sodium has 11 electrons around it, which would make one valence electron, so 1 electron on its outer shell, which would have been right here. And how it wanted to get rid of that electron so that it could have a full valence shell and be cool like the noble gases. Then we also discussed how chlorine wants to gain 1 electron because right now it has 17, so it has 7 on its outer shell, and how it wants to have 18 so it can have, again, a full outer shell and be cool like the noble gases. So, okay, so if we have one element that wants to lose 1 electron, and then we have another atom of another element that wants to gain 1 electron. Well, I mean, the easiest thing to do would be for sodium to just give chlorine 1. Then sodium is happy, chlorine is happy, and everybody's happier, basically. So that's actually just an ionic bond. That's what's going to happen. So this 1 electron, this 1 valence electron that sodium has, is going to leave sodium, as you can see, and then it's going to go over here to chlorine. So that's this electron. And chlorine, which previously had 7, which are the white electrons, is now going to have 1 additional red electron from sodium, and it is going to be happy. And sodium, having lost the electron, is also going to be happy. So, okay, we're giving electrons away, we're getting electrons, but how does that make a bond? Well, remember how sodium has 11 electrons, as we can see here, but it also has 11 protons. So previously 11 negatives, 11 positives, because electrons are negative and protons are positive, they canceled each other out. So it was neutral. But having lost 1 electron, it actually has a positive charge, because as of right now, it has 11 positive protons and 10 negative electrons. So we can see that there's 1 bonus positive charge, and sodium is an ion, which basically just means like a charged atom because it has lost or gained electrons. For chlorine, the opposite happens. Previously, it had 17 protons and 17 electrons, so it was, kind of happy because it was just neutral. But when it gains the extra electron, it's going to now have, I'll write it over here, it's going to now have still 17 positive protons, because remember, the protons, they just stay in the nucleus. They don't leave. They just stay there. And now it's going to have 18 negative electrons. So it's going to have an extra negative electron. So it's going to have a negative charge, and sodium is going to have a positive charge because of it lost 1 electron. So we talked about how opposites attract. So the positive sodium and the negative chloride are actually going to attract each other just based off of their charges, and that's what makes the bond. So an ionic bond, you can think of it kind of like magnets, because we have a positive, we have a negative. They're not like physically connected to each other in the way that like, oh, I'm gonna grab some glue, or like I'm gonna grab some tape and tape them together. It's not like that. They stay together because they're attracted to each other, not because they're kind of like physically connected in the way that, you know, like they stay together in the way that magnets would, instead of in the way that, again, you would tape or glue something together. And these are stronger than covalent bonds, which we're going to go over now. And again, ionic bonds, think of it like magnets. Positive and negative charges attract because somebody loses electrons and somebody gains electrons. So covalent bonds is kind of the opposite in the way that instead of giving or receiving electrons, electrons are actually shared. So if we look over here, our example is actually water. So we have oxygen has 8 electrons, but remember, it wants to have 10 so that it can have a full outer shell. And each hydrogen has 1 electron, but it wants to have 2 because the first shell only has 2 electrons, like that's the capacity, and they both want to have full shells. So oxygen wants to gain 2 electrons, and hydrogen wants to gain 1 electron each. But since there's 2 hydrogen atoms, I'm going to put a times 2 there. Again, each hydrogen wants to gain 1, but since there's 2 of them, hydrogen kind of in total needs to gain a total of 2 electrons. So what's going to happen is oxygen is going to be like, okay, you know what? I need to kind of say that I have 10 electrons, but I don't mind if you use them sometimes. Like we can share them, you know, and hydrogen is like, well, okay. So what happens is that hydrogen, right, where I'm going to do them in red, hydrogen has this 1 electron, and it says to oxygen, okay, you know, I will share it with you. Instead of just being my electron, now it's a shared electron. You know, we both have it. And the other hydrogen is going to do the same. So there, oxygen kind of gains 2 borrowed electrons, right? Because it has the 8 that it had, the 8 weight electrons that are oxygens, but now it's also getting to share some of the time this red electron from this hydrogen and this red electron from this hydrogen. And so oxygen's happy now because, I mean, if you count 1, 2, 3, 4, 5, 6, 7, 8, the borrowed electrons also count. It has 8 on its outer shell, so now it's happy. But we don't just need to make the oxygen happy, the hydrogens need to be happy too. And right now, they only have 1 electron each, so only the red ones. So oxygen says, okay, well, I mean, you're not going to be able to see blue, so here. Oxygen says, okay, since you let me borrow these 2 red electrons, I will let you borrow 1 of my electrons as well. So it's going to give this green electron, it's going to share it with, oh, you really can't see that very much. Here. This now purple electron, it's going to share it with this hydrogen, and this other purple electron is going to share it with this hydrogen. So now everybody's happy because the hydrogens have 2 electrons each, shared or not shared, you know, it doesn't matter. All you need is 2 electrons each. And oxygen has 8 in its outer shell for a total of 10. So, I mean, I know that I said oxygen needed to gain 2 electrons and hydrogens each needed to gain 1 electron, but in reality, they don't need to have the electrons just to themselves. A shared electron counts as a full electron. You know, they want to have a full outer shell, but it doesn't matter if you're sharing one of the electrons or not. It doesn't matter. Like, atoms are going to do ionic or covalent, and either way, they're going to end up happy. So like what I'm saying is, I know that it might seem like kind of like, well, you know, you don't have the electron, you're just sharing it. So how is it full? But shared electrons do count. All right, and these are kind of, you can kind of think of this as ionic. If ionic is kind of like magnets, covalent is kind of like rope. Like they stay together because hydrogen is grabbing onto these 2 and oxygen is also grabbing onto these 2 electrons, and then same here. You know, hydrogen is grabbing onto these and oxygen is also grabbing onto these. So it's kind of, rather than charges like ionic, in covalent, it's more like, well, since we're sharing this electron, we have to stay close enough so our electron clouds overlap. you can kind of see the overlap of oxygen's electron layer, what am I saying? Electron cloud and hydrogen's electron cloud. So again, this is kind of like, if ionic is magnets, covalent is kind of like rope or tape or something like that. They both use the electrons, which is why they both have a full shell. And also something curious to notice is that ionic, in this example, we have sodium, which is a metal. We can tell because, well, it's found in the first column of the periodic table, but also because, you know, in this case, it says alkali metal. Versus chlorine is a halogen. That means that it's a non-metal. It's just being more specific, kind of. And so based on that, we can see that ionic bonds happen between a metal and a non-metal. While covalent bonds, we can see oxygen is a non-metal, hydrogen is also a non-metal, so it's going to happen between two non-metals. So this is because for ionic, metals usually want to lose electrons, while non-metals want to gain electrons. So this is kind of like, okay, you know, you want to lose, I want to gain, and we can do an ionic bond and everyone's happy. While, again, if it's a non-metal and a non-metal, they both want to gain. So the only way for them to both be happy is a covalent bond. So that's kind of the reasoning behind it. And, you know, in the kind of live camp, we would be doing a brief lab, and I'll put the link in the description, so definitely check that out. It's really cool. And now we're going to kind of go over how to balance chemical equations. So I found this video on YouTube, which is of course not mine. You know, credit goes to the filmer. And it is actually really cool. So I'll just go ahead and play it.
How to balance chemical equations in 5 easy steps. Step 1, count the atoms on each side of the equation. Let's count each type of atom. Sulfur, I have 8. Oxygen, I have 2. On the product side, sulfur, I have 1. And oxygen, I have 2. Note that if there's nothing after an element, we assume that to be 1. And that's it. We're done with the first step. Smooth. The big rule for balancing equations is that we can only change the coefficients. Those are the numbers in front of the atoms. The numbers after the atoms, the subscripts, cannot be changed. So let's balance this equation by changing the coefficients. If there's no coefficient written, we assume that it's 1. So right now there's a 1 in front of each of these terms. We can see that we have 2 oxygens on each side of the equation. So the oxygens are fine, but the sulfur atoms, we have 8 on the left side, the reactants, and only 1 on the right. Well, to fix that, I can change the coefficient in front of the sulfur on the right and make that an 8. So if I put an 8 here, that means 8 times the 1 sulfur, that'll give me 8 sulfurs. And now my sulfurs on both sides are 8, but this 8 here is also times the 2 oxygens, and that gives me 16 oxygens. So I've fixed the sulfurs, but the oxygens aren't balanced. I can change the coefficient here, though, to 8, because 8 times 2 equals 16. So now I have 8 sulfurs on each side, and I have 16 oxygens on each side of the equation. This equation is balanced. Step 3, so you don't forget, only change the coefficients. Let's try another problem. So in this equation, we have 2 hydrogens, 2 oxygens, over here 2 hydrogens, and 1 oxygen. How about, let's see, I'll put a 2 right here. So 2 times 2, that gives me 4 hydrogens, but 2 times the 1, that'll give me 2 oxygens. So my oxygens are balanced now, but my hydrogens are messed up. What I can do over here is put a 2 in front of hydrogen, and now 2 times 2, that'll give me 4. And now the atoms on each side of the equation are the same. This equation's balanced.
So again, really great video. Credit goes to the creators of the video. I find it really useful to kind of show how to balance chemical equations, and we're going to be doing some examples. All right, so the first thing that I want to do is kind of see how many atoms there are on each side of, each type of atom, just to begin with. So remember, if the number is in front here, it kind of applies to the whole thing. So for example, if I were to have a number in front here, it would apply to the sodium, which is Na, and to the chloride, which is Cl. But these small numbers only apply to the atoms that they are directly following. So for example, this 2 here means that we have 2 chloride, but it does not affect Fe, which is iron. So again, the kind of big numbers in the front affect everything after it. Well, everything in the molecular compounds. But the small numbers only affect the elements kind of directly in front of it. All right, so now that we've covered that, I'm gonna just briefly kind of count. We have 1 sodium over here, because if there's nothing, we assume it to be 1. So there's 1 sodium, because we have a 1 here, and then since we don't have a subscript, it's called, since we don't have a small number and it's also 1, we just do 1 times 1, and that's just 1 sulfur. Then we also have 2 chlorines, because since there's nothing here, we assume it's a 1, and since there's a 2, we multiply 2 times 1, and that's just 2, so that's 2 chlorine atoms on this side. That's just to start with. Is there any way I can make this bigger? Yes, there is. Okay, awesome. And over here, we're going to just do the same thing. Since we don't have a subscript for sodium, we say that it's a 1. And since we don't have a big number in front, then we also just assume it to be 1. So we have 1 sodium. And same thing goes for chloride. All right, awesome. So now we're going to see if, they kind of match up. Well, we have 1 sodium and 1 sodium, so that's okay. But here we have 2 chlorides and only 1 chloride over here. Since we're not allowed to change the subscripts, we can only change the coefficients. To get this to be 2, we're going to have to put a 2 here. Because by putting a 2 here in front, we grab the 1 chloride and we multiply by 2. So that gives us 2. And remember, since it's a coefficient, since it's one of the big numbers in front, it also applies to the whole thing, kind of. So sodium is also multiplied by 2. And here we also get 2 sodiums. Okay, so now chloride is happy because we have 2 chlorides here, and then we have 2 chlorides here, so we're happy with that. Now the only problem is sodium. Over here we have 1 sodium, and over here we have 2. Well, that's okay. We can just kind of mess with this coefficient. Again, we're not allowed to touch the subscript, so we just don't touch that. But if I put a 2 here, oh, okay, that was not my intention. If we put a 2 here in front of the sodium, then we have to multiply the 1 times 2, and then we get 2 sodiums. Now we just do another check to make sure that kind of everything is accounted for. We have 2 chlorides, okay, that's good. And then over here we have 2 sodiums and 2 sodiums, and we are happy because the equation is balanced. We have the same number of each type of atom on this side and on this side. So the reactants and the products, but we'll get to that in a few videos. So, and okay, well now let's do this one. This one seems a bit more complicated because we have more subscripts, but it's okay, we'll figure it out. The first thing we're gonna do is count the original number on each side. So over here we have 1 Fe. Fe is iron. We don't have a coefficient, we don't have a subscript, so we can just assume it's 1. We also have 1 hydrogen, again, no subscript or coefficients, and 1 chloride. again, no subscript, no coefficient. It's pretty easy when there's no subscript and coefficient, so that's good. And then over here, okay, we have 1 iron. Remember, since there's no big number, we assume it's 1, and this small number, this 2, this subscript, it doesn't affect the iron. It only affects the thing that kind of is directly in front of it, and in that case, it's chloride. And speaking of fluoride, we have 1 for the coefficient times 2 for the subscript. Again, only affects chloride. So that would be 2 chlorides. And over here, we have no coefficient for hydrogen and a 2 as a subscript. So we have 1 times 2 is 2 hydrogens. All right, now we're ready to kind of see what matches up and what doesn't. All right, we have 1 iron, 1 iron. Okay, that's good. Oh, here it seems I kind of switched the order a little bit, but that's okay. That's 2 hydrogens and 2 chlorides. All right, but here we kind of start running into an issue because we have 1 hydrogen and 2 hydrogens over here, so they don't match up. And then here we have 1 chloride and here we have 2 chlorides, so again, that doesn't match up. So what we're gonna do is, well, okay, so we need 2 hydrogens and 2 chlorides, right? And we can't add a subscript, we can only add coefficients. Well, since hydrogen and chloride are together and we need to kind of get them both from 1 to 2, I'm just gonna put a 2 here. Because, okay, iron is unaffected because, you know, this plus kind of separates. This iron is not part of the hydrogen and chloride molecule, which is actually called hydrochloric acid. But of course, you know, I didn't expect anyone to know that. So then since we have a 2 here as a coefficient, we multiply the hydrogens times 2 to give us a total of 2 hydrogens on this side. And here we also multiply the chloride by 2 because since it's a big number, a coefficient, it affects both of them. Chloride times 2, and that gives us 2. All right, and now we're gonna start seeing what matches up. Well, we have 2 hydrogens over here, 2 hydrogens over here, so that's good, we fixed that. 2 chlorides over here and 2 chlorides over here. We fixed that, great. And then also just 1 iron on this side, 1 iron on this side, so we're done. It was as easy as just adding 1 coefficient, even if it looked a little bit more complicated. So yeah, that's it. And one other note I would like to make is sometimes, for example, originally we had the chlorides, like it was, you know, 1 on this side, 1 on this side, they were balanced, but sometimes you kind of have to mess it up a little bit in order to fix it. For example, sodium was also originally balanced up here, you know, 1 sodium, 1 sodium. But to balance out the chlorides, we had to kind of mess with that a little bit, and that's okay. You know, if you need to make it unbalanced to later make it balanced, that's perfectly fine. Like, it happens all the time. All right, and now we're going to do some more examples. Here in the live camps, we'd be moving into breakout rooms. All right, so here we have what seems to be a more challenging one. All right, so here we have carbon and hydrogen plus O2, which is oxygen gas, gives us water, H2O, and carbon dioxide, CO2. We call it carbon dioxide because it's carbon, and then di means 2, so it's dioxide because it's 2 oxygen. So I don't know, I think that's cool. All right, so here I've kind of already counted out all the atoms of each type. So we have 1 carbon because no coefficient means that there's a 1 there and there's no subscript as well. We have 1 hydrogen because of those same reasons. Oxygen has no coefficients and a 2 as a subscript, so we do 2 times 1 is 2. And then on the other side, we have 1 carbon, again, it's over here, just no subscript, no coefficient, so it's just 1. We have 2 hydrogens because we have no coefficients and a 2 is a subscript, so 2 times 1 is 2. And here's where it gets a little bit trickier because this 3 oxygen is not that easy. We get 1 oxygen over here with the water because, again, no coefficient and no subscript, so that's a 1, plus these 2 oxygens, no coefficient, and a 2 is a subscript, so we have a 2. Now, obviously, I know that you guys know that 1 plus 2 is 3, but I'm just going to put that there because when we are balancing, you know, like here we have a 2, here we have a 3, but since it's found in more than one place, we have to remember that, and that usually means that it's a better idea to leave it for last. We don't worry about the oxygens until we balance the carbons and hydrogens. So that basically is kind of just to, you know, because we can change this or this, it's kind of, I like to leave it for last. Just, you know, get the easy stuff out of the way and then worry about the oxygen. All right, one carbon, that's okay for now. We might have to change it later, but for now it's okay. 1 hydrogen here and 2 over here. So what we're gonna do is we're gonna, remember, can't touch the subscript. So we're gonna add a 2 as a coefficient. And we are going to have to multiply the carbon by 2. So that gives us 2 carbons, which, you know, again, it used to be balanced, now it's not, but that's okay. That just happens sometimes. We'll fix it in a second. And then we also have 2 hydrogens. All right, great. So now the hydrogens are balanced because we have 2 on this side, 2 on this side, but now the carbons are unbalanced, so we have to take care of that. So we have 2 carbons on this side, and we have 1 on this side, and again, can't touch the subscripts. So I'm going to put a 2 as a coefficient, so we have to multiply 2 carbons and then the 2 oxygens by it. So we multiply this by 2, and we get 2 carbons. And now here comes, oh, that's a very messy 2 right there. Just gonna redo it. There we go. All right, so here comes the tricky part because this coefficient affects hydrogen. Oh, sorry, it does not affect hydrogen. This coefficient affects carbon and oxygen, but it doesn't affect the full 3 oxygens. It only affects this one. So instead of having 3 oxygens that are 1 plus 2, we're actually going to have 1, which is this oxygen right here. We don't affect it. It stays just 1, plus these 2 oxygens affected by this 2. So we're going to do, oh dear, okay. My handwriting just keeps getting messier and messier. I'm sorry. Here. So we have this 1, which is this oxygen, plus 2 times 2, because it's these 2 oxygens multiplied by this coefficient. So that's our total right now. So our total would actually be 5 oxygens right now. Can I change this to, no? Okay, change the whole thing. That's okay. I'll just make a new text box. All right, so our grand total right now is 5 oxygens because this one is unaffected, and then we have 4 over here. Okay, so now we just need to balance it out. We have 2 oxygens, we have 5 oxygens. Can't touch the subscript. And now we run into a problem because you can't multiply 2 by a whole number to get it to be 5. Because like 2 times 1 is 2, 2 times 2 is 4, and 2 times 3 is 6. We already skipped over 5. So what we're going to do is we are going to multiply it by a fraction. Okay, you know, let's just, we need 5, we have 2. We have this coefficient right here. So I'm actually just going to put as a coefficient 5 over 2. So what that basically means is if we have 5 halves of an oxygen and we multiply it by 2, then the 2 kind of cancels out this 2 that the 5 is being divided by, and that gives us 5 oxygens. So this whole thing, 5 halves molecules of O2, gives us 5 oxygens. Okay. So we have 2 multiplied by 5 halves. That's a little weird though. Gives us 5 oxygens. And technically here we are balanced, by which I mean we have 2 carbons on each side, 2 hydrogens on each side, and a grand total of 5 oxygens. That kind of reads like 50, but it's 5O because 5 oxygen, and then 5 oxygen on this side as well. Yay, okay, so we're done, right? Not really. There's no way to have 5 halves of an oxygen molecule. Like, what are you gonna do? Chop one in half and leave it in there? That would not work. You know how they tell you in math that like, oh, you know, sometimes you need to round up because you can't have half of a person, or you can't buy half of like a watermelon or something. Actually, you probably can buy half of a watermelon, so don't use that example, but what I'm saying is we can't leave fractions as our coefficients. So what are we gonna do? We have everything balanced, and you know, I don't want to go through all the work of having this be a different number and then having to change everything. So I'm going to show you guys a little trick. We need to get rid of this 2 in the denominator of the fraction. So what we're going to do is we're going to grab the entire thing, going to put some parentheses around it, and put a 2. What does that mean? Well, I'm multiplying everything, and by everything I mean the coefficients of everything. So this 2, this 5, this 1 that's over here, remember, since there's not anything, we say it's a 1, and this 2, we're grabbing everything and we're multiplying it by 2. So what's that going to give us? Well, we used to have 2 CH, but now we're going to have 2 times 2, 4 CH. Okay, plus, we used to have 5 halves of oxygen, but of O2, but since we multiply that by 2, now we're just going to have 5 O2, and there is a small 2 here. I'm just going to do it like that so that no one's confused. Okay, and that is going to give us, with my beautifully drawn arrow, kind of, I guess, we used to have 1 molecule of water, so 1 H2O, but now we're going to have 2 H2O. And again, there is a small 2 over here, and I'm just doing it in black so as to not confuse with the coefficients. So we have 2 H2O, plus we used to have 2 CO2, which is carbon dioxide, but now we're going to have 2 times 2, 4 CO2. All right, well, this right here is our final balanced chemical equation. So this one, even though it might have looked not as complicated, was actually pretty complex. But you know, we just kind of stuck to the basic rules of first figure out how many atoms of each type there are on each side, and then kind of, you know, start balancing them. And if there's something in 2 places, like the oxygen here was in 2 places, just leave that for last. And we got an answer, so yay. And now it's time for my favorite part of the day. It's cookie application time. So where we basically grab everything we learned for that day and we apply it to cookies, because cookies are awesome. All right, so in part 1 of the video, or well, you know, the previous video, we talked about physical versus chemical changes. So, and both of these changes happen in cookies. So basically, we're just gonna think about the type of changes that happen when cookies are baked and also when cookies are broken, or when, you know, you break them or something. So, you know, write down your answers and then I'll go over that in a sec. And then also sodium bicarbonate is one of the ingredients of cookies. You might know it as baking soda. The chemical formula is NaHCO3. So this is sodium, hydrogen, carbon, and 3 oxygens. Heating sodium bicarbonate, so if we add heat to it, causes it to decompose into water and carbon dioxide. So basically, we have here sodium bicarbonate. We add heat to it, a chemical reaction happens, and we get these three products, or we get these three things as a result of the chemical reaction. So go ahead and try to balance the equation. And then I'll also go over that. So just, feel free to pause the video and try it yourself. All right, well, now we're going to talk about the different types of changes. Well, when we bake a cookie, we are adding heat to it. The cookie's molecules are kind of rearranging themselves. Chemical reactions are happening. Like, for example, the chemical reaction that happens with heating sodium bicarbonate. This reaction right here is happening during the baking of cookies. And also, since we can't unbake cookies, it's not something that you can reverse. This is a chemical change. And then when we break cookies, we're not really adding heat or anything to it. All we're doing is changing the shape and size of the cookie and the cookie pieces. And it's still going to behave the same way. For example, it's still going to, if you leave it in the oven for too long, for example, whether it's broken or unbroken, it's still going to burn and it still tastes the same, basically. So since we're just changing the physical properties and no reactions are taking place, this is a physical change. And then here we have the sodium bicarbonate equation. So we're going to figure this out as we have figured out the previous equations. So here we have sodium, hydrogen, carbon, and oxygen. So we're just gonna write down what we have of each. We have one sodium because, again, no coefficient means that there's one, well, no coefficient and no subscript. And since it happens for sodium, hydrogen, and carbon, we can say that we have one of each. And then oxygen, we have the 1 for the coefficients and the 3 for the subscript, so we have 3 oxygen atoms here. I'm just going to move this up a little bit. So you can, there we go. And now we're going to do the same thing for this side. Here we have sodium with a 1 as a coefficient and a 2 as a subscript, so we have 2 sodium atoms, and we can see that it's not found anywhere else. Okay, then we have hydrogen. No hydrogen here or here, it's over here in water. And no coefficients, a 2 is a subscript, so we have 2 times 1, 2 hydrogens. For carbon, we have this carbon over here, which has no subscript, no coefficient, so that's 1. And also we have the carbons from carbon dioxide, which again, no subscript, no coefficient, so that's 1. So we have 1 plus 1, 2 carbons. And again, I understand that 1 plus 1 is 2, but that's just to help us remember that there's carbon in 2 different places. And now we have oxygen. Oxygen is actually found in all 3 of these molecules. So we have no coefficients and 3 oxygen. 3 is a subscript, so we have 3 times 1, 3, plus 1 oxygen with no subscript or coefficients. So that's 1 oxygen there, plus also 2 is a subscript, no coefficient. So that's 2 oxygens there. So we have a grand total of 6 oxygens. Okay, that's a lot. Okay, so remember that I said that when we have elements that appear in more than one place, in more than one molecule, like in this case, the carbon, which appears here, and the oxygen, which appears in all of them, we leave them for last. We try to solve everything else first. Okay, so we have 1 sodium here, 2 over here. So we're gonna put a 2 in front right here. And that gives us 1 sodium times 2 is 2. And then this 2 applies for all of these. So we have the 1 hydrogen times the 2 is 2 hydrogens as well. We have the 1 carbon times 2 is 2 carbons. And the 3 oxygens, we multiply the subscript times the coefficient, so that's 3 times 2 equals 6 oxygens. And now Something amazing has happened. Somehow, just by adding this two, look at this equation. It is insanely complicated. You know, like oxygen appears in 3 different places. Carbon appears in 2. There's 6 oxygens, you know. But somehow we have managed to already balance the equation. Because look, 2 sodiums on this side, 2 sodiums on this side, 2 hydrogens, 2 hydrogens, 2 carbons, 2 carbons, and 6 oxygens, 6 oxygens. So that's it. All we needed to do was put a 2 there. And that just goes to show that sometimes, even though chemistry might seem a little bit complicated, it's actually somewhat simpler than you think, or than it appears at first. And I also have made a Kahoot for this video and also the previous one. So basically just like a day 1 recap for Kahoot. I'll put the link in the chat. And yeah, that's all for today. Hopefully you enjoyed day 1 of Intro to Chemistry and Cookies. Well, see you for day 2.